A uniform electric field of magnitude E is parallel to the positive x-axis. Show that an expression for the potential difference between 2 points separated by a distance d on the x-axis is given by delta V is equal to the product of the magnitude of the electric field and the distance between the 2 points. Let's start with a sketch of our electric field. It says that our electric field is parallel to the positive x-axis. So we will have the x-axis being horizontal and the y-axis being vertical. We know that this is a uniform electric field, so I will depict this uniform electric field with parallel electric field lines. These electric field lines are directed to the right. In this uniform electric field, we are to find the potential difference between 2 points on the x-axis. So we'll pick 2 arbitrary points. We will say we have an initial point being x0 right here, and we have our final point x0 plus the distance between the points. So in other words, this difference here is equal to d. Now, we're to show that the potential difference is equal to minus the magnitude of the electric field times the distance between the 2 points. To show this, let's start off with the relationship that we know between potential difference and electric field. The potential difference is just minus the line integral from some initial point to some final point of the electric field. Here, the electric field has a magnitude that is a constant magnitude, and we will say it points in the x along the positive x-axis. While our displacement, well, let's look at what our dr vector is going to be. We're moving from our initial point on the x-axis to our final point on the x-axis along this path indicated. We will have a small displacement differential along that path, which I'll call dr. And since our path is parallel to the x-axis, this little bit of differential is going to be equal to dx I hat, a tiny bit of change along the x-axis. So this means that our dr vector is equal to dx I hat. So we have the change of potential, the potential difference between points A and B is equal to the dot product between the electric field and our displacement differential. So this is the dot product between the electric field given by E I hat and our displacement differential given by dx I hat. This is our potential difference from A to B is equal to E dx times the dot product between I hat with itself. I hat being a unit vector and having a magnitude of 1, when we take the dot product of it with itself, we end up with the value of 1. This gives us the potential difference is equal to minus E, that comes outside of the integral, times the integral from our initial position at point A, which is only along the x-axis, so we'll say x0, to point B, which is x0 plus the distance d, dx. When we integrate this, we get minus EX from x0 to x0 plus d. This means that our potential difference is minus E. Our final position is at x naught plus d. Our initial position is at x naught. And the x naught minus x naught cancels. And we get the potential difference in a uniform electric field between 2 points separated by a distance of d is equal to minus the magnitude of the electric field times d.